To get extremely precise, we astronomers refer to this as a blob, or smudge. From this vantage point, it might not seem like much, but what do you expect from something that is so close to the actual edge of the observable universe? You would A. be at the beginning of time and B. be gazing upon a whole galaxy with a massive black hole at its center if you were present when this light was released. We have semi-directly spotted the most distant black hole to date. In addition to being cool in and of itself, this one smudge might have provided the answer to the question of where our universe's supermassive black holes came from. Presenting the Able 2744. Approximately 4 billion light-years away, there is a massive group of galaxies. Cosmologically speaking, it's essentially our backyard. What's behind Able 2744 is more fascinating than what's in the cluster itself, at least for us now. Over its 4-million light-year expanse, the cluster is surrounded by a massive halo of dark matter that distorts space. Deflected and amplified light from far-off objects passing through the cluster. Because of the cluster's incredible gravitational lens, we can see far farther than would be possible with our small, man-made telescopes. For this reason, Able 2744 was one of the first things the James Webb Space Telescope had to study in depth using the Hubble Space Telescope. Our smudge became intriguing at this point. The object displays IR colors consistent with a galaxy whose normally visible light has been stretched out by the expanding universe, increasing or redshifting its wavelength by a factor of more than 10, according to JWST's deep infrared observations. A redshift of 10.1 indicates that this light has been traveling for around 13.2 billion years, reaching us from a time close to the beginning of time, when the cosmos was less than 3.5% its current age. A higher redshift indicates a greater distance. Because of this, our smudge was given the moniker UHC1, or Ultra-High Redshift Galaxy Number 1, where Z stands for redshift. That's awesome, but galaxies much farther away have now been discovered by JWST. When we aimed another orbiting satellite towards the smear, it was the truly thrilling part. The Chandra X-ray telescope captured this image. As it happens, this small clump is emitting a ton of X-rays. Since X-rays are now much more difficult to focus, the 4 X-ray light pixels are originating from someplace inside this area rather than from all over it. The only known explanation for a galaxy ejecting X-rays at this intensity is that it is home to a quasar. To refresh your recollection, a quasar is the result of the supermassive black hole, SMBH, which is the central component of all galaxies, beginning to feed. Matter becomes superheated as it spirals in the direction of the black hole, surpassing the brightness of the entire galaxy. And just before it hits the black hole, things get so frantic that high-energy X-rays shine brightly in the vacuum outside the black hole. We may calculate that the black hole must have a mass 40 million times that of the Sun based on the distance and the amount of X-ray emission. That is 10 times the mass of the SMBH in the Milky Way. In addition to being the earliest known quasar and, hence, the first black hole for which we have proof, UHC1 is the most distant quasar ever found. Now that we've cleared that out, let's move on to the exciting part. Understanding the formation of supermassive black holes, one of the most contentious topics in cosmology, is necessary to appreciate why UHC1 is so fascinating. A black hole that is 100,000 billion times the mass of the Sun is found at the center of almost every galaxy in the current universe. Much smaller black holes, known as stellar black holes, are also visible to us. These can range in mass from roughly 10 to 100 solar masses. Strangely, black holes in the middle of the 100 to 100,000 range are not visible to us. We'll return to the reason that's peculiar. We now know how to create stellar black holes, which are created when a big star dies and its core collapses in on itself. What is the growth mechanism of supermassive black holes? The key question is that they might have grown from the earliest star corpses in the early universe, consuming gas and combining with other black holes over billions of years to become as massive as they are now. However, as we have been searching farther and farther away over the past 10 or so years, we have begun to discover quasars that are fueled by supermassive black holes that shouldn't have had enough time to grow that large. These quasars are from the first billion years of cosmic time. This puzzle can be solved in two different ways. The black holes were either tiny at first and developed far more quickly than we had anticipated. Or they began considerably larger than the black holes that develop in the current universe's stellar deaths. These are the models for heavy and little seeds, respectively. UHC-1 will assist us in selecting one of them. First, let's look at the little seed model. In less than a billion years, can a stellar corpse develop into a quasar engine? Well, it's difficult. Even with an infinite supply of gas, a black hole can only feed so quickly. Radiation is released as gas spiraling into a black hole heats up, pushing on the gas falling in and opposing the black hole's gravitational pull. Although larger black holes have the capacity to consume and emit more, there is always a rough top limit that rises with mass. This is known as the Eddington limit. A black hole that feeds at this maximum pace for a billion years would develop to a size that is insufficient to account for those early quasars. Nevertheless, we can use a number of strategies to get the little seed model to function. In some cases, black holes can feed more quickly than the Eddington limit, but they still have to feed continuously to become supermassive, which is problematic in and of itself. Another option is to create many black holes near one another and have them rapidly merge. Alternatively, you may begin with really massive stars that left behind black holes that are perhaps 100 or even 1,000 times bigger than those created today. Smaller stars form in the modern cosmos as a result of the fragmentation of gas clouds caused by the heavy elements expelled in previous supernovae. However, as the cosmos collapsed, the pristine hydrogen and helium that had first filled it stayed together, most likely producing enormous stars and similarly huge but not supermassive black holes. It is feasible to create supermassive black holes in less than a billion years by combining these two strategies: rapid and steady feeding and large stellar black hole seeds. The lack of black holes in the 100 to 100,000 solar mass range is still not explained by this. You would think that some stragglers would still be in that region if SMBHs grew from stellar black holes by passing through it, but that doesn't appear to be the case. The heavy seed model is what we should try. What if the extremely dense cores of deceased stars weren't even the source of supermassive black hole seeds? The idea that highly dense matter is necessary to create a black hole is completely untrue. A black hole must be formed when a mass of a given mass is crushed into a specific size. The Schwarzschild radius is this. It is around 3 kilometers for the Sun, and a solar mass compressed inside that radius would have the same density as a normal mountain that is 3,000 meters high compressed into a cubic centimeter. Conversely, the Schwarzschild radius of a typical chunky supermassive black hole with a mass of 1 billion solar masses is equivalent to the orbit of Neptune. Cotton candy would be the density of a billion suns packed into that area. Yes, a massive black hole would form instantly if a solar system were filled with cotton candy. As far as we know, cotton candy was not present in large amounts in the early cosmos. However, it was teeming with gas that would eventually give rise to galaxies and stars. The protogalactic clouds that resulted from the collapse of that gas to create those objects might have had cores that were dense enough to collapse straight into black holes without ever producing a star. Once more, this is only effective in the early cosmos, where the uncontaminated helium and hydrogen do not have a tendency to break apart during collapse. It turns out that theoretical estimates of these direct collapse black holes' masses fall close to 100,000 solar masses. This allows us to bypass the middle range of stellar seeds and move directly from gas to the tiniest SMBHs. Furthermore, a tiny SMBH can grow into a huge SMBH in a matter of hundreds of millions of years with a fairly reasonable feeding rate. It appears that the heavy seed model seems more likely to be true than the little seed model. Therefore, let's hear what UHC-1, our newest player, has to say about this. Prior record holders for the most distant quasars, such as J1342 + 0928, J0313-1806, and J1007+2115, are all similarly enormous and have already placed a great deal of strain on the small seed formation idea in recent years. But assuming some extremely inventive astrophysics to allow a really cosmic bulking phase, they were all discovered at about 700 million years after the Big Bang, right on the edge of the time required to grow a tiny seed. However, UHC-1 reduces the permitted growth time by 200 million years. Growing a little seed into an SMBH used to seem just about conceivable, but today it seems almost impossible. To try to give this more substance, let's take a closer look at this item. We can estimate the ratio of quasar light to starlight in this object using the JWST photos. Quasar light dominates even those photographs. The galaxy's star mass is about 40 million suns, which is the same as its black hole mass. This is about 1,000 times less than the Milky Way's star mass. In and of itself, this is not remarkable. Galaxies from so long ago should still be accumulating mass and turning gas into stars, according to our expectations. However, during the majority of the universe's existence, there has been a strong link between a galaxy's star count and the mass of its core black hole. Some have interpreted that as evidence that galaxies and their center black holes evolve in a relatively lockstep. Contrary to what UHC-1 indicates, the black hole begins comparatively massively and subsequently the stellar mass catches up. UHC-1 might be the first of a new class of objects known as an OBG, or outsized black hole galaxy, which stands for overly massive black hole galaxy. OBGs are things that are thought to have existed in the early cosmos when the masses of stars and black holes were roughly equal. This sort of object may no longer be hypothetical, given the amount of X-ray and infrared light from UHC-1 is compatible with predictions of OBG production. That tells us a lot, if it is. Only when their central black hole is created via direct collapse rather than by the development of a stellar remnant do OBGs function. In general, the heavy seed model appears to be doing well, while the little seed model is doing somewhat worse. It's not quite a smoking gun, though. For instance, UHC-1 might be strange. Its SMBH might have evolved in a unique setting, such as a quasistar, or from a rare and huge primordial black hole. However, these other explanations would tend to be disfavored, at least in the case of UHC-1, given how well measurements of the region match the direct collapse and the OBG model. Furthermore, other supermassive black holes could have arisen from tiny seeds even if UHC-1 is an OBG. However, the evidence supporting the latter as a significant source of SMBHs is generally being disproved. What comes next, then? Well, we continue to search. The first of its kind is UHC-1. However, in astronomy, where there is one, there are frequently many, and we should soon discover the many. The more distant glimmers of the earliest stars and quasars that initially illuminated a newly born spacetime that JWST and Chandra find, the more we will be able to piece together what the early times were like.